On October 29th, 3I/Atlas will disappear from sight as it slips behind the Sun, echoing Avi Loeb's bold assertion that this enormous, high-speed interstellar visitor might perform a concealed adjustment to bind it eternally to our solar system. Authorities insist it's merely a temporary comet. However, preliminary observations render that explanation difficult to accept. Imagine a core potentially spanning 20 kilometers in diameter and tipping the scales at over 33 billion tons, all without displaying any detectable non-gravitational acceleration amid intense gaseous eruptions. Should Loeb's theory hold, we're on the cusp of observing the inaugural interstellar guest to linger among us, with no means to monitor the pivotal instant. What secrets will evade us amid that solar eclipse? And whose perspective will prevail once Atlas returns into view? The date of October 29th marks an unyielding divide on the timeline. That's when 3I/Atlas enters the dazzling zone obscured by the Sun, severing access for all terrestrial observatories. The alignment proves unforgiving. Earth, the Sun, and the comet aligned precisely, leaving our world blinded by the radiance. Over almost 6 weeks, the heftiest interstellar entity ever identified will traverse invisibly, its trajectory and potential shifts concealed from scrutiny. This observational void extends far beyond a mere logistical hiccup. It ensures that crucial events, like perihelion, the Sun's nearest pass, and any prospective orbital shift, will occur entirely out of our reach. The Earth-Sun separation measures roughly 150 million kilometers. During conjunction, Atlas glides just past that at 1.36 astronomical units. No surface-based facility can disentangle its dim light from the Sun's overwhelming blaze. Orbiting instruments such as Hubble and JWST must stand by too, their protective measures activating against the hazards of solar proximity. Consequently, a void in information persists from late October until early December. Position tracking, light spectrum studies, and even simple luminosity checks all cease. Slim chances for partial sightings lie with select solar spacecraft and coronagraph instruments, designed primarily for solar flare investigations rather than remote comets. Their resolution and capture rate struggle to detect something as subdued as Atlas. For the majority of researchers, visibility ends precisely when the narrative's most vital segment unfolds. All inquiries regarding organic departure or deliberate retention, whether it's a natural body or an artificial construct, linger unresolved in this imposed quiet. Time presses on, and the decisive phase will transpire unobserved by any eyes. Avi Loeb's interest sharpened instantly upon reviewing the initial light measurements. The preliminary dimension assessment for 3I/Atlas, 20 kilometers in width, struck with explosive impact. To put it in perspective, 1I/Oumuamua was under a quarter-kilometer long. 2I/Borisov, the prior interstellar comet, extended to about 1 kilometer at most. By contrast, Atlas dwarfs them by a full magnitude beyond what detection programs anticipated as an opener. This dimension wasn't speculative. It derived from the object's luminosity, adjusted for range and illumination angle, then compared to established comet shine properties. With an apparent magnitude exceeding 12 and lacking a thick, light-scattering envelope to inflate the figures, the inference stood firm. The core must indeed be substantial. Loeb's doubts stem directly from the calculations. Detection forecasts suggest that for each sizable interstellar arrival, hordes of tinier, dimmer counterparts ought to have appeared beforehand. Efforts like the Atlas Survey, Pan-STARRS, and the Vera-C, Rubin Observatory sweep the heavens nightly, calibrated to snag these swift, solar-avoiding intruders. Still, the initial pair of interstellar finds were modest. Then, abruptly, a behemoth surfaces. Under any distribution framework, the probabilities stretch credulity. Assuming the scale assessment endures, it implies either overlooked swarms of diminutive objects or an occurrence that's extraordinary and unaccounted for. Here marks the launch of Loeb's case. A 20 kilometers interstellar body emerging so promptly after the earlier duo challenges the power law projections that form the backbone of contemporary detection efforts. The statistical red flags blared not from Atlas's visibility, but but from its immense proportions clashing with astronomers' prior assumptions about interstellar populations. For Loeb, that solitary metric, 20 kilometers, emerged as the initial and starkest irregularity amid an expanding catalog. A weight of no less than 33 billion tons now cements 3I/Atlas's place in the annals. This estimate, derived from motion simulations and the comet's steady illumination, overshadows all prior verified interstellar travelers. But the contradiction ignites right there. Even with robust venting at 100 to 150 kilograms per second, chiefly carbon dioxide, no non-gravitational acceleration registers. In cometary studies, this poses the quintessential propulsion puzzle. Expelled gases function as impromptu engines, nudging the core faintly from its gravitational forecast. Standard comets reveal such influences through positional records, a gradual shift, a gentle bend from strict orbital pull. Yet the Minor Planet Center's worldwide compilation, encompassing more than 4,000 location fixes, detects zero such variance for Atlas. The ceiling on its non-gravitational the acceleration falls below 15 meters per square second, so minimal that sustaining the observed behavior demands an extraordinarily hefty body to stay so stable. These figures intensify the inconsistency. Consider the recorded gas output, factor in the expulsion speed, and divide by the projected mass. The anticipated propulsive thrust ought to show up in observations, barring a core that's not just enormous but unusually compact, or emissions that cancel out symmetrically across every axis. Computer models using Monte Carlo methods explore all reasonable variations in core dimensions and compactness. For cores under roughly 5 kilometers in diameter or sparser than 1,000 kilograms per cubic meter, the calculations fail. Expelled gases would have deviated Oumuamua from its forecasted route ages ago. Nothing short of a colossal, solid entity aligns with both the photometric and orbital data. Other ideas, such as opposing jets or a cluster of barely connected debris, demand exquisitely calibrated dynamics and unlikely configurations. The standard theory grapples to align the data without resorting to rare coincidences or contrived fixes. To Loeb and his team, this isn't mere trivia, it's a compelling prompt. With confirmed mass and negligible thrust, pathways to artificial origins stay ajar. Astronomical surveys rely on vast datasets. For each behemoth like 3I/Oumuamua or Atlas, statistical forecasts suggest the cosmos ought to teem with countless dimmer, tinier extrasolar drifters. The reasoning is straightforward. Diminutive items vastly outnumber the big ones in all documented meteoroid and comet populations. Assuming detection systems function properly, initial interstellar finds should skew toward the minuscule, those that eclipse giants by factors of thousands or more. Yet the observations paint another picture. The Pan-STARRS survey, the Atlas Array, and soon the Vera-C, Rubin Observatory have combed the heavens for years, cataloging millions of sightings. Their precision now catches objects mere tens of meters wide, provided they're zipping along briskly enough to register. The inaugural pair of interstellar visitors, Oumuamua and 2I/Borisov, match this pattern, both compact, subdued, and barely detectable. Then Atlas materializes abruptly, at least 20 kilometers across, over 33 billion tons, shining well beyond the faint limit. No flock of petite relatives, no steady escalation in scale, just a stark probabilistic jump. Experts modeling populations crunch the stats. If 3I/Atlas represents the norm, hunts should have netted hundreds or thousands of punier specimens already. But the tally stands at 3. Researchers from Pan-STARRS and Rubin highlighted the discrepancy in confidential reports, noting the likelihood of spotting a Titan ahead of its dwarf peers is cosmically slim, under 1 in 10,000 per certain calculations. The power law scaling, fundamental to size hierarchies, seems fractured. The cosmos must be concealing hordes of elusive, low-light travelers, or Atlas stands as an anomaly appending all priors. To anomaly hunters, this transcends oddity. It's an indicator that core assumptions in the data falter, and 3I/Atlas's narrative is already reshaping paradigms. Path projections for 3I/Atlas trace a route skimming the ecliptic, inclined by just 5 degrees. For a newcomer from beyond the stars, such congruence is highly atypical. Even local comets and asteroids, born in our system, trace paths that veer and loop across the sun's domain. A haphazard interloper from afar should cut in at a steep incline, its route molded by the disorder of remote stellar realms. Yet Atlas sails nearly flush with the orbital plane, navigating a lane typically claimed by native denizens. The setup turns odder under scrutiny. In the lead-up to closest solar approach, Atlas chains a string of brushes with key worlds. On October 3rd, it passes Mars at under 29 million kilometers, a tight shave by cosmic yardsticks. The pattern persists. Its course later veers near Venus and Jupiter, amassing a chain of planetary grazes uncommon beyond scripted probes. Specialists in orbital mechanics compute the figures and deem the cumulative probability for such a bulky, swift traveler to nail this exact sequence vanishingly remote. A single near approach per world is rare. 3 consecutively plunge the odds below 1 in 1,000. This setup isn't trivial. The ecliptic-hugging arc positions Atlas ideally for tidal influences. Every planetary swing might subtly alter its velocity or curve its arc. But the deeper puzzle concerns how these layered passes prime the solar rendezvous. The path feels calibrated, as though engineered to optimize prospects for a bold pivot at perihelion. For investigators probing the divide between chance and design, the voyage itself serves as a mute testament, posing dilemmas that raw data can't resolve. The initial photographs from the 3 observation groups monitoring 3I/Atlas revealed something unexpected. Rather than the anticipated trailing tail, a focused radiance on the side facing the sun took center stage. This intense light persisted despite all efforts to account for motion blur or equipment glitches. Experts reviewing images from Gemini South and the VLT scrutinized the information intensely, hunting for engineering flaws, yet the lopsided pattern remained intact. As the comet drew nearer to the sun, that radiance dimmed, and a standard tail started to extend outward, consistent with solar wind effects. A few experts dismissed it as mere optical illusion, while others viewed it as evidence of genuine transformation, maybe a shell cracking apart or an abrupt eruption from hidden depths. Chemical specialists turned their attention to the comet's composition. In a tight time frame right before solar conjunction, JWST's near-infrared spectroscopy recorded a volatile mix that upended forecasts. Carbon dioxide greatly exceeded water at almost an 8:1 proportion. Among solar system comets, water typically leads as the primary volatile. Such a balance suggested a core either kept in icy stasis from its interstellar origins or blanketed by carbon dioxide ice. Verification groups recommended restraint, labeling the outcome tentative pending additional evidence to validate or refute it. Hypotheses proliferated. Certain researchers proposed a carbon dioxide shell protecting a water-laden core inside, while alternatives blamed impurities or analytical mistakes. Discussions overflowed into overnight Slack chats, with each group staunchly upholding their views. Then, toward the end of September, a vivid green glow suddenly swept across the coma. Observations from both hobbyist and expert skywatchers confirmed the alteration, linking it to C2 or CN molecules glowing under solar UV light. Usually, this green hue emerges close to perihelion for comets, but in this instance, it showed up ahead of schedule and more vividly than anticipated. The hue shift sparked fresh inquiries into the arrangement of volatile ices and the comet's outer makeup. Layer upon layer of oddities, visual, compositional, and color-based, piled on layers of doubt. As the comet vanished behind the sun, resolutions remained deferred, its essence caught midway between illusion and discovery. Avi's scenario depends on a fleeting interval that's hardly noticeable on the universe's timeline. At perihelion on October 29th, 32/Atlas will zip along at close to 44 kilometers per second, an interstellar projectile curving a mere 1.36 astronomical units from the sun. For anything following a hyperbolic trajectory, this represents the sole instant when even a minor velocity adjustment, a shift of merely a few km/s, might shift the outcome from fleeing to orbiting. The principles are relentless. To pivot from an escaping interstellar path to a stable solar system loop, Atlas would require about 8 kilometers per second of delta V applied precisely at closest solar approach. Less than that, and the comet speeds away for good. Should such an adjustment occur, it would go undetected. Solar brilliance overwhelms all ground telescopes. Superior orbital coronagraphs would still battle to spot a dim, swift amid the sun's glare. These tools' sensitivity tops out at magnitudes 8 to 10, insufficiently sensitive for something like Atlas amid solar conjunction. In reality, any path alteration, any flare of activity or deliberate propulsion would evade notice until the comet reappears after several weeks. The close pass by Mars, only 29 million kilometers away on October 3rd, sparked momentary optimism for straightforward observation. Mission coordinators weighed the odds, crunching figures on visual scale and luminosity. The math closed off the prospect. From that range, a 20 kilometers body spans under 0.15 arcsec, below the resolution threshold of Mars orbiters. As a mere dot of light, Atlas would still prove too dim to capture. Nothing in the way of details, outflows, or deployed instruments. Even Mars' premier imaging system can merely observe the void. To Loeb and his allies, this unavoidable obscurity poses both irritation and potential. If an intervention is made, its proof will embed itself in the comet's path, ready for analysis once Atlas returns to sight. Tom Statler, NASA's top expert on minor bodies, lays down a firm boundary amid the evidence. It appears comet-like. It behaves like one. In nearly every aspect, it mirrors the familiar comets we study. That's the foundation. The prevailing opinion places 3I/Atlas, albeit uneasily, among the diverse, chaotic group of ordinary comets. Peculiar mass, chance oddity, quirky elements. Comets are chaotic by nature. Path irregularities and close planetary passes. Serendipity amplified by cosmic scale. Specialists such as Karen Meach and Kwanzaa reinforce this perspective, citing observational biases, incomplete discovery records, and the erratic nature of ice-heavy objects. For them, the onus falls entirely on the unconventional hypothesis. Allo tackles identical information from the contrary angle. He avoids a structured metric, but builds his reasoning by accumulating irregularities. Mass, dimensions, ecliptic positioning, planetary brushes, makeup. The tighter these traits align, the more compelling the rationale for scrutiny. In Elle and Joe's perspective, once a sufficient number of peculiarities accumulate, the prudent course is to intensify scrutiny, particularly during uncommon occurrences like a perihelion transit obscured by the sun that might obscure a pivotal adjustment. He avoids quantifying it, yet the underlying logic is straightforward. As the catalog of irregularities expands, approach the entity with the gravity of elevated risks. The upcoming key opportunity arises in early December as Atlas reappears following solar conjunction. Leading observatories worldwide will be geared up to examine shifts in its trajectory, spin, and composition. Come March 2026, with Atlas approaching Jupiter, another wave of observations will evaluate if its course persists as hyperbolic or shows alterations. This evaluative approach focuses not on tallying deviations, but on monitoring verifiable, testable forecasts. Should the path adhere to expectations, the conventional explanation prevails. Otherwise, discussions will shift to uncharted territory. At present, the sole assured element is that the narrative hinges on the insights gleaned from data once the observational hiatus concludes. On October 29, 2025, 32/Atlas will slip behind the sun, halting all terrestrial monitoring right when Loeb posits that a retrograde binding operation might secure it within our solar system. Its approximate 20 kilometers diameter and minimum mass of 33 billion tons, paired with minimal non-gravitational influences and a carbon dioxide to water proportion approaching 8:1, challenge conventional profiles for an organic extrasolar comet. Nevertheless, as things stand, no concrete proof substantiates an engineered provenance. NASA's stance continues to emphasize that comets often display erratic traits, leaving enigmas like the origins of its verdant spectral signature and the authentic character of its flight path unanswered. Upon Atlas's December return, Updated orbital parameters and molecular indicators will deliver the ultimate verdict. In the interim, unwavering vigilance and candid scholarly discourse remain essential.